So hello everyone, in this video we'll be solving another LeetCode problem, and the problem name is count the number of computer unlocking permutations. So let us read the problem first. So you are given an array complexity of length n. There are n logged computers in a room with labels from 0 to n minus 1, each with its own unique password. Then the password of the ith computer has complexity of I. The password for the computer labeled 0 is already decrypted and serves as the root. All other computers must be unlocked using it, that means using the 0th computer or previously unlocked computer with this following information. You can decrypt the password for computer I using password for computer J, where J is any integer less than I. That means J should be less than I if you want to unlock this ith computer. Also, there is some additional information given with lower complexity such that J is less than I and complexity of J is less than complexity of I. Then to decrypt the password for computer I, you must have already unlocked the computer J such that J is less than, and same thing. In the end, we need to find the number of permutations that represent a valid order in which computers can be unlocked, starting from computer 0 as the only initially unlocked one. And since the answer can be very large, so you need to mod it with 1e9 plus 7. So in the end, you need to return the total number of how many total permutations can be formed, and you need to return the answer with mod by this, because there can be a lot of combinations, so it can go above the range of the integer numbers. So that's why you need to mod with 1e9 plus 7. So what the question is saying, that you have given computers labeled from 0 to n minus 1. Initially 0th computer is already unlocked, and you need to find total number of permutations in which you can rearrange these computers and you can unlock each and every computer. Initially 0th computer is already unlocked, so you can use this computer to unlock any other computer. And as we move forward, you can use any other computer which is already unlocked to unlock another computer which is currently logged. And to do that, you have a condition that if you want to unlock some ith computer, then you should choose the jth computer which is less than I in index, and also its complexity of J should be less than complexity of I. Also, this jth computer should already be unlocked. It should not happen that this jth computer is logged. So this is what the question is saying. So let us understand in more better way with the help of examples, and let us find how to let us derive how the solution would actually work out. So let us see the first example. So yeah, this is the first example with we have been given the complexity as 1, 2 and 3, and how many permutations can be possible, that we need to find out. Initially this is the 0th computer which is already unlocked, this is the first and this is the second computer. Now this complexity 1 is lesser than complexity 2 and complexity 3. So we can, and also this index J is also lesser than both of these index. So we can use this particular 0th index to unlock this computer as well as this computer. So we can say that okay, one arrangement can be like 0, 1, 2, where we have unlocked this computer. What can be the another possible combination in which we can unlock the computers? We can first unlock this computer and we can then unlock this computer. So we can arrange this computer in this manner also, 0, 2 and 1. So these are the two possible combinations by which we can unlock these computers based on the given conditions that the question has provided, such that J should be less than I, complexity of J should be less than complexity of I, and also this jth computer should be already unlocked. So in this case we have used 0th index to unlock computer, so this 0 was already unlocked, so these both the criteria gets fulfilled. So one thing we can make sure that okay, we can always use this 0th computer to unlock any of the computer, because this is already unlocked. So we just need to rearrange, we need to just find out how many permutations can be formed. But this is not as easy as you as it seems, because there is one scenario, because the question is also said that there might be like some scenarios in which you might not be able to like find any permutations, because then in that case you need to return 0, and this is what the second example looks like. So let us see the second example and try to understand what is the scenario in which we won't be able to unlock all the computers. So the complexity looks like 3 3 3 4 4 and 4, 0 1 2 3 4 and 5. These are the indexes. Initially this is already unlocked, so we can unlock 4, we can unlock this 4, and we can unlock this 4. Yes, we can unlock these, but we cannot unlock this 1 and we cannot unlock this 2. Why? Because the question is said that this complexity of j should be lesser than complexity of I, not less than equal to, strictly less than. But here you can see that these are these are equal to this complexity of 0, so we cannot unlock all the computers due to these two computers. So that's why in this case we won't be able to find any permutation, so we'll be returning 0 in this case. And you can see the output is also 0. Previously it was 2, so we find out 2 permutations. In this case we won't be able to unlock all the computers, so that's why we are returning 0. So this is the case where we won't be able to find out any like permutation. So what is this case? Case 1. If anywhere in the complexity array you find that any number, so any complexity of I is equal to complexity of 0, in this case we can surely say that we won't be able to unlock all the computers, because we won't be able to find any unlock computers which can like just unlock this one. So in this case we will be returning 0. What would be the case 2? Case 2, we can simply say that we can use 0th computer to unlock all the other computer. So in this case answer exists, but what would be that answer? Let us see. So we can say that okay, this 0th index will be fixed. We have the other choices to make. So let's say there are n elements in total. So we have already fixed one element, and no matter what number comes here, we are only using this 0th computer to unlock each and every computer. So we can say that okay, we can place n minus 1 elements here, we can put n minus 2 elements here, we can put n minus 3 elements here, we can put n minus 4 elements here, so on and so forth. In the last we would be able to put only one computer here. So in total these many permutations will be possible. And what is this? This is nothing but n minus 1 multiplied by n minus 2 up till we got 2 multiplied by 1. So this is nothing but factorial of n minus 1. So if answer exists, answer would be nothing but factorial of n minus 1. So we will be returning that. Otherwise, if this is the first case, we would be returning 0. So this is how the solution for this problem would work. So let us see the code now so that we can understand in more better way. So yeah, this is the code. Initially we have declared n as the size of the complexity array, and then we are first checking whether we find any element which is lesser than or equal to complexity of I. So why? We have seen that for case 1. So if we found any element, any ith complexity which is less than, this is not equal to, this should be less than equal to. So yeah, I did one mistake. So yeah, if this is less than or equal to complexity of 0, that means for sure we cannot in any case unlock this particular ith computer. So in that case we need to return 0. So first we are checking that only. If we find any element whose complexity is lesser than or equal to our 0th element or the 0th computer, that means we cannot find any permutation. So in that case we will be returning 0. Otherwise we can say that okay, we can surely have one answer. And what would be that answer? That answer would be nothing but n minus 1 factorial. So we are finding that only. We are just calculating n minus 1 factorial. So we will be iterating from 1 up till n minus 1, and we are just multiplying it by I, and we are taking care of the mod because question has said that like it can be happen that answer can be very large, so you need to stay within this integer range, so you need to mod it by 1e9 plus 7 to remain in the integer range. So that's why we are just taking mod, which we have just declared here. Initially our answer would be 1, so we are just multiplying to get the factorial n minus 1, and we are taking care of mod. In the end we are just returning this answer, and that would be the nothing but total permutations formed. So yeah, that's it about this solution. I hope you learned from this video. Thank you for watching.